All right, mic check, mic check. All right, looks good. All right, so we're going to pick up where we left off on the flood modeling that we were doing. So I'm back here in my ArcMap. We have the TIN that we created, the triangulated irregular network. So what do we want to do? Well, we also have our LAS dataset. And what we wanted to do before anything is extract our own digital elevation model. So this one here came from Kentucky GeoPortal, but we want to be able to do a little more and use our own stuff. So we're going to look at what we have to do that. And it's pretty easy. There's a tool simply called LAS2DEM, LAS dataset to raster. And we just have to give it that LAS, okay? Elevation is what we're after. And as far as the output goes, the cell assignment is what you're after. So if you took average, it would average out just all the points in the cloud. So the surface stuff, the bottom stuff, you know, everything would be in the cloud. But what we're after here is the minimum. So we want the terrain, right? The terrain, the water surface, and the exact ground layer of the watershed that we're looking at. And then this linear field, this supposes that the requested output of this raster is, say, smaller than your input data's spatial resolution would be. And in this case, if there weren't enough available points, it would interpolate some. And you have a few ways here. And if you look over on the right-hand side or click that tool help button, you'll get more information about approaches here, especially as it results to how it's going to handle voids and all. Okay, but we're going to go minimum, and let's see. We'll just leave all of that as it is. We'll just leave all that as it is. I didn't give it a good name here, but I'll just use that. So that's what we have there. And unlike the DEM that we got from surface, see, we could have did an analysis to start pulling these buildings and stuff out of there. However, because we're going to be looking at flood, the volume of those buildings is going to be very important. And history's shown us that failure to include that means that you're not going to get the flood field that you're looking for. So let's just have a look. So there's our basin bottom there. Okay, there's our own DEM. And it matches up pretty well. Just ours has the buildings in it, footprints of stuff that, and they haven't been extracted. But that's okay. All right, so there's that. So I'm going to go ahead and just remove that one from the Kentucky GeoPortal, and this is now the one that we're using. Okay, so that's step one out of the way. Now, if we can shift gears a little bit, remember we ended up with this TIN, and this is supposed to tell us where the water surface is right now, right? And the question is ultimately going to be, as more and more water continues to pour into this basin, we're after which areas are going to get flooded first, right? So obviously, where the river is at currently, it's just going to continue to fill. But then as it begins to spill over in, you know, outside of the river channel, where is that water going to go? Now the water surface 10 I created here only covers a small area, but it doesn't matter. The steps would still be the same, and the calculations would pretty much be the same as well. All right, so what do we do? So what are we after? Well, all we have to do, really, it's quite simple, is take the difference between this TIN model and the underlying digital elevation model. And the difference is exactly how much water has to fill to start to make that spot. So let's work the math out a little bit, and that'll be a little more clear. Now, we can't directly calculate the difference between the 10 and the elevation model. We have to first convert that 10 into something else. Oh, my dog's going crazy. So we have a from 10 tool set here, all right? And you have some options. So these are different things you could do, but down here, second to last, we have 10 to raster, and that's what we're after. So give it that 10 that you created here. We'll just leave that. Yeah, we'll just leave everything as is. All right. So there's that, and it may look a little different. We'll just put some color back to it so that it looks how it did before. Okay. And now let's take the difference. Okay. Let's take the difference between those using the raster calculator. And let's see, we want to know water surface from there. So surface minus water surface. All right. And let's just call that the difference. And notice we're not putting an extension on it. The grids seem to work pretty fast and don't give us any trouble. But if you were exporting this out for use in R or something, I would recommend that you did .diff. Oh, it says it already exists because I did this already. Let's as we should all be doing here is we got to give it explicit permission to overwrite. I think that's going to be in my environments here. No, it's going to be in options. Overwrite the outputs. And now we'll bring up that. Hit the wrong little button. So surface minus water surface. And we want to call it diff. All right. So now let's have a close look at that. And you'll start to see that it's pretty close to what we want already. So let's just give it some good variation here. Yeah, I think that's okay. Right. So what does this tell us? Okay, what does this tell us? Let's make sure we're looking at the right one. All right, so these values here that are in the water channel, okay, for the most part, this is the water surface, and these values should be close to 0. As you go higher and higher over the crest of the shoulder along the river channel, the area covered by the water will increase as you go up the shoulder. So each unit increase in the Z value, okay, is directly convertible to the amount of rainfall that's fallen into the water basin, okay? So the amount of rainfall times the area of your basin gives you the volume, okay? And we can calculate here how large our river channel is, right? So, right. So you give it a value of the depth of the channel, right? At what value is it still in the water? And then you can calculate what volume of water is needed to fill that. So each unit increase of water coming into the basin has to have an equal area to spill out into. So you could set this up and ask the question, you know, for each 1 foot increment increase, say we're starting at 0, right, where this difference is, this is where we're starting. So for each increase in Y, how much rainfall is needed, right? How much rainfall is needed to be able to make the water occupy that large of an area? And here the answer is shown clearly. You can see the channels that start to fill, and then as it gets closer to the orange, as it begins to spill over the channel. So how you set up your question will dictate how much land here is flooded. All right. so this is what you have to get to once you have this difference map. Okay, then you can figure out in 1 foot intervals how much rainfall is needed to flood X amount of area. And I'll stop this video here, and then we'll fall back to that and pick up once more.